Yeah. Okay. So this is where we are. Chapter 4. We finished the summary of the quantum theory. And we finish with the statement analogous to the one in chapter 3 that for an arbitrary spacetime metric there is no preferred quantum representation, in the sense that there is no preferred notion of vacuum, one particle Hilbert space, and of focus space. So we have a bunch of them, infinitely many, and all of them at the same footing. So what I want to do now is to repeat what we did in chapter 3, and is to consider two different Fock representations. So consider two different Fock representations, and I want to relate them to see what is the relation between them. So what we have is, on the one hand, we have the space of complex solutions with a split that they will call S1 plus S minus 1. The other Fock representation is based on a different split of the space of complex solutions. And here we have our basis. I'm going to call basis 1 with index I. So basis is always orthonormal. So I don't write it, but I think it's orthonormal. We have our creation and annihilation operators. In this case, annihilation A1, which we can obtain as usual, projecting on the field operator with the corresponding positive frequency mode. And our vacuum, we will call vacuum 1, which is annihilated by all these guys, our one particle Hilbert space and focus space. And here we have the same orthonormal basis of, so basis of S2 plus, we have our annihilation operator, which is the basis. Our vacuum, our one particle Hilbert space, and our focus space.
Iman?
Prayesh?
Yeah, the brightness of your pen is a decreasing function of time. So,
Thank you.
yeah.
Can you see this?
Can you point again?
Can you see what is written right now?
Yeah, we can see this. Yeah.
Okay.
Yeah, it's better. Thanks.
Okay. So one comment, remember that this notation was kind of too simplistic because, phi hat is really an abstract operator, and we find a representation here and a different representation here. So now, because there can be confusion, let me write explicitly the representation 1, or representation in the focus space 1 of this operator, and representation of this operator in the second focus space. Whenever there is no confusion, I will not write the R, but whenever it can be. And in this section, I will keep it explicitly. So, our goal is to see, our goal is find a unitary operator U that goes from the first focus space to the second focus space. You know what a unitary operator is. Unitary operator is that its adjoint is equal to the inverse. This is what we mean by unitary operator, in case you don't remember. So we look for a unitary operator between these two Fock spaces such that that maps this guy to this guy, and the same for the momentum. This is what we want. An operator, unitary operator that brings this representation to this representation. And we want to study its properties. And study its properties. This is our goal here. So in the following, I will assume that U exists. Assume U exists, and I will ask, and I will come back to the question when it exists in the next section. So in this section, I will assume that it exists. As in chapter 3, the key information, key info is encoding the relation between bases. Basis phi 1 and phi 2. And the trick is the following, since if I take the basis of S1 plus together with the basis of S1 minus, we know that this is a basis of the complete space of solutions. There always exists complex coefficient alpha and beta, complex constant coefficients, so they don't depend on time, such that phi 2 can be written as a linear combination of the basis 1. The existence, this equation is guaranteed by the fact that this is a complete basis. Now it's a bit more complicated than in the case of the single harmonic oscillator, because now the basis has more than one element, so we need an index for the basis 2, an index for the basis 1, and therefore the coefficient alpha and beta carry two indices. In the harmonic oscillator, where no indices here, and therefore alpha was just a number. Now alpha is a matrix, which is in fact infinite dimensional matrix. And where the coefficient alpha ij can be obtained by taking phi 2 and extracting this coefficient, so we have to multiply by phi 1j, and beta ij, similarly, we have to multiply by minus 1 complex conjugated j. And this is what we call Bokoliubov of coefficients. So this is the definition of Bokoliubov coefficients, and they really encode all the information between the two quantum theories and of this unitary operator that I am looking for.
That's a 1 and a 2 right there, right?
That's a 1 and a 2, right?
Yeah. Okay.
Right, because if I take the 2, this guy, and I multiply by 1 conjugated, this one will kill this guy because they are orthonormal, and this guy times this guy is minus 1, so this is equal to minus beta coefficient.
Okay.
So the coefficients alpha and beta are not completely arbitrary because this basis is orthonormal and this basis is orthonormal, so that information is encoded also in the alpha and beta. So orthonormality of both bases imply the following relation. Remember, just remember, in the case of the singular harmonic oscillator, this was the relation between them. Now it's more complicated. But we have two. We have alpha I sum of k, alpha ik, alpha star, jk minus beta ik, beta star, jk. This is delta ij. If you only have 1 degree of freedom, this reduces to this expression. And that is another one which has to do with the fact that this guy and this guy are orthogonal to each other, which is alpha ik beta these are the relations that they must satisfy. The second one, in the case of the harmonic oscillator, is trivial because if you don't have indices, this is something minus the same equals to 0. Only when you have indices, this is non-trivial. So that didn't appear for the harmonic oscillator. So I want you to check that this is true, to derive this. And as I said, the hint is simple. Hint here is phi 2, phi j2 is equal to I delta ij. This, if you substitute this expression here, you get that directly. And the hint for this one is phi 2 I phi 2 j complex conjugated. This is it. So let me put numbers to the equations. Calling this equation 10, this equation 11, and that's all. So this was the defining equation for alpha and beta. We can also write the inverse. The inverse is how to write phi 1. Maybe I should write the x dependence here, x dependence here, and x dependence here, just to emphasize that these guys are coefficients. They are just numbers. So all the x dependence here, and there, the same here. So the inverse transformation is the following one. One has to be careful with the indices because they are here in a different order. Alpha star I phi j2 minus beta ij alpha star 2 j. Here the j index goes with the first one in alpha and beta. I told you I have to be careful. And here the j1 goes with the second one. So that's different.
Wait a minute. What's the sum over I when there's an I on the first thing?
J. I also want you to check this. By the way, remember next week there is no class. No class next week. If you want, a good way of remembering how it goes is using, just as a parenthetical remark, one can use this matrix notation. I like it just because I remember with it where the indices goes. Two complex conjugated. We have said that this is like alpha. Alpha now is a matrix, so I am just suppressing the indices. Beta is another matrix. Beta conjugated, alpha conjugated, acting on phi 1 j, phi 1 conjugated j. And this equation 10, just tell us that the determinant of this matrix of matrices is equal to 1. And the inverse, which I'm writing here, is the inverse of this matrix. The inverse of this matrix is what we are obtaining here, is A with conjugation and the indices change in order. So this is the admission of the adjoint of alpha, because we are conjugating it and changing the order of the indices. So it's taking the admission. And this is minus beta. I am not changing beta. I am not conjugating, but I am changing the order, so I have to take the admission and take the conjugate to compensate. So this is just the transpose. I am transposing the matrix, and here is just this and alpha star. So this is equivalent to that in this matrix notation. Is it okay?
These have indices and
sorry?
These have indices.
Right, these guys are like matrices.
Oh.
So I am suppressing the indices, yes. This is why I am transposing them. So this is a matrix of matrices.
Okay. So this is 2D-dimensional. If there are n i's, then there's 2n-dimensional matrix.
Right, but there are infinitely many i's.
Yeah,
I know. It's a huge matrix, so I am just...
And when you write the Bogoli-Bott coefficients, so it appears that phi I2 and phi I J1, they are at the same space-time points. Or
right.
So, okay.
Right. They are. So
right.
This is a solution of the wave equation. This is a solution. This is also a solution. Of course, you take the Klein Gordon operator here. It will act on here without here, giving 0. And,
yes.
so it's at the same point. So now, as we did, just in chapter 3, we can say here that the relation between basis vectors, the phi 1i and phi 2i j and the conjugated, so these two relations imply also a relation between annihilation and creation operators. That relation is the following. So the annihilation operator in the focus space 2, labeled by the index I, is I'm going to leave here some space because I'm going to write something here. Sum of j alpha I j conjugated a1 j minus beta star I j a dagger 1 j. And now maybe you can tell me what is missing here. Dagger. Any guess? Sorry? Did you say something?
No.
You said something. Dagger. G. I hope I'm wrong thing. This is right. So why I leave here some space?
It's for you, right?
Right.
You and
Right.
and you.
Remember that I didn't write anything here in chapter 3, and then I make a comment saying that this is a bit simplistic because, you know, this is an operator on the focus space 2, this is an operator on the focus space 1. Sorry. No. Sorry. I am writing here the inverse. I didn't say. I am writing here just the inverse transformation. A2 dagger is obtained from here just taking the Hermitian conjugated.
Wait, so which ones of those are stars and which ones of those are daggers?
Coefficients are stars because they are complex numbers. Operators are daggers.
Okay, so that's a star on beta on top.
Exactly, and a dagger on the operator. And this is just the inverse of this transformation. The relation between A2 dagger is just obtained from here, taking dagger here. So you take here this out, dagger, this out, and that. And what I was saying is that this is an operator on the focus space F2. This is an operator on the focus space F1. So it is not really consistent to equate them. Where I need to go is to write this. And you. This guy takes an element of F2 and brings me, because U goes from 1 to 2. So I minus 1 takes an element, takes an element from here to here. You operate with A2 and then you go back to F1. Therefore, this equation is consistent. And for this one, equation is 12, and this equation is 13. So where is this coming from? Let me prove it, at least let me prove the first one. The proof is simple, you know. Imagine I start with this operator. This operator, by definition, can be computed as the inner product in the space of classical solutions of the solution 2 together with the field operator in the representation 2. And now what I want to do is to multiply both sides by U in this way, because this is what I have in the left-hand side of the equation. So I'm going to prove the equation 12. So what I will have here, both sides with U minus 1U, but all this, so this guy is a function, a classical function, the only operator is here. So the U minus 1 and U will go directly to hit the operator. The other stuff is transparent to it. But remember that what we want the operator to do is to, is to take R1 and give me R2 and vice versa. So this is just R1 of I. This is what I want the operator to do. So I am looking for an operator doing that, so I can substitute that equality. So therefore, I can write in this side, I can use now the equation, I didn't put a number, this equation, to write this guy as sum over j alpha ij phi 1j plus beta ij phi 1 conjugated j, multiplication with R1, which is sum over I of 1 hat I phi 1 I plus dagger I phi 1 I conjugated. But this product is not difficult. So we have a linear combination of phi 1 star, multiplying a linear combination of phi 1 and phi star. Phi 1 and phi star are orthogonal, so this first term times the second term will be 0. This second term times the first one will be 0. So only first with first, second with second will be non-zero. And phi 1j, phi 1i is a delta ij that will kill one of the sums, and that will give me sum in j. Sorry, I should use here a different index. Sorry, because I am using I here. So that will kill me one of the sums. I will be left with alpha I j a1 okay, and the other one will give me a minus because this guy and this guy give me a minus with beta I j conjugated, because remember, sorry, this is also conjugated here, because the inner product is antilinear in the first entry, and I should have here A1 dagger well, J if I am right. Which agrees with what I wrote here. This is similarly, you can prove equation 13. Okay? So let me put a box on the important equations because I know this is a big pack, but I have to write big. And the board is not clear. So these are the important equations, relation between the two operators, the two operator and the ones, and the same for the daggers. So the conclusion that we can obtain from here is simple, is that if the beta coefficients are different from 0, then this guy has some combination of A1 dagger, and the values, let's say, are beta. So conclusion from here is, therefore, if beta coefficients are different from 0 for some I and j. That is, if the positive frequency modes have some contribution from the negative one frequency node, then the states vacuum 1 and vacuum 2 are different states. So what I should say is that the state, when I bring it to the focus space 2, are different. I can only compare them if they are in the same Hilbert space. So in order to compare them, I have to take vacuum 1 and bring them to the focus space 2. Otherwise, I cannot compare them. So the state 1 is not the vacuum in F2. So the two vacuums are different states. Indeed, we can compute the number of quanta in the mode phi 2I contained in the state, in the vacuum state 1. So in order to prove, to really show explicitly that this guy, the vacuum 1, is not the vacuum in the focus space 2, I can ask how many quanta this state, vacuum 1, has in the mode phi I2. So in order to do that, I have to take the expectation value of this state, of the number operator in the focus space 2 corresponding to the mode I. You know what the number operator is? Number operator is just A2 dagger A2. There is no sum here. No sum. So we can compute the number. Do you guess how to compute that number?
You can write A2 in terms of A1.
Right. A2 is A1, equation 12. But here we have use. In chapter 3, we didn't have the use and everything was simple, but the use was explicit. Now my question is, can you do it explicitly with the use?
You put a U,
You put a U
inverse U
U
in the middle.
Right. You put here a unit, which is U minus 1, and then you use the equation. But U minus 1 is just the identity, and then I have U minus 1, A2 dagger U, I can use the expression, or the dagger of the expression, and U minus 1, A2 U, I can use the expression. And so the U's disappear, I only have vacuum 1 and A1 dagger, and if you do the computation, you will obtain the beta coefficients squared. But now we have a sum that we didn't have in the case of the singular harmonic oscillator. The singular harmonic oscillator was just beta squared. And this is also a check for you. So you don't miss me during the whole week. So this makes manifest that the state 1, O1 is not a vacuum in the focus space 2, and also tell us how to interpret the beta coefficients. They have the interpretation of data square is how many quanta there are in the mode 1. So this is good, but I mean, this tells us information about how the state 1 is in the focus space 2, but just one expectation value. Sorry.
Is the expectation value of the number operator 2 in the vacuum 2 the same as the expectation value of the number operator 1 in the vacuum 1?
0,
Okay.
because they are the vacuum.
Okay.
So if you ask in the focus space 2, how many particles are in the vacuum 2? 0.
Okay.
If you ask in the focus space 1, how many particles are in the vacuum 1? It's 0.
In general, if you choose a different vacuum, are observables the same in that different vacuum as long as you're choosing the same operator for the observable in that vacuum?
Only if the unitary operator exists. So the question is yes, if this U really exists.
Okay.
And your intuition is precisely the definition of unitary equivalent quantum theory. So I will explain it later, but if two representations are unitary equivalent, it's because of that. Because one state here, you take any expectation value, and you can reproduce with another state here the same numbers using some operator. So it's a good question. Okay, but this is just one expectation value. So I would like to really know how the state 1 really looks like exactly in the focus space 2. So what I want to do is to obtain the explicit form of the state, the vacuum 1 in the focus space 2. And it can be obtained from the following equation, as we did in the first chapter. So you start by applying annihilation operator on the vacuum 1, annihilation operator 1 in the vacuum 1, this is 0, by definition of vacuum 1. Now I can insert here U's and U minus 1, so this is going to be the same as I want the U the other way around. So maybe I got wrong here. No, sorry. No, right. So this is the same as U A1 I U minus 1 U vacuum 1 equal to 0. Obviously, this is just identity, and if that was 0, this is also 0. But now I can use equation 13. So using equation 13, this is the same as sum of J alpha Ji A 2 J minus beta conjugated A2 dagger J, this acting on U1 equals 0. And now from here, doing exactly what you did in the chapter 3, one can obtain the expression for this state up to a normalization. In this case, it's a bit more difficult because you have indices, but it's exactly the same. So, therefore, this implies that the vacuum 1, when mapped to the focus space 2, is the exponential of two-particle state. The only thing is that we have now two indices here that we have to sum over. J acting on the vacuum tube. As before, M is just a normalization factor. And Vij is just beta, so sum over k beta ik conjugated times alpha kj minus 1. So it's an exponential of a two-particle state. So vacuum, 2 particles, 4 particles, 6 particles, etc., where the coefficients are ratios between beta and alpha, as in chapter 2. Let me just make a comment about this. Because now that we are in infinite dimensions, one has to be careful because all mathematical issues. So let me just to say without proof that it is possible to prove. It is not difficult, but not simple either. One needs a few lines. That alpha as a matrix. Let me put, I don't know what notation to use. Or the indices, I don't know. Let me put this fancy alpha and this fancy beta to indicate that they are matrices, are bounded operators in wherever they act, and also that alpha inverse exists. Just using the properties of alpha and beta, the box that was I think here, one can prove that these guys are bounded and that the inverse exists, because it is not trivial that it exists in general. I'm not going to prove that because it's just some detail, but just to tell you that can be proven, and you can look the literature with you. So this is the state explicitly. Now you can understand why I did the example of the harmonic oscillator, because here with sums use, if this is the first time you see this, it is quite easy to get lost. So I think it is quite pedagogical doing it first in a simple case when you understand what is going on, and now this is just a matter of adding more sums and indices, but the physics is very, very similar. So another property important is that equation 11 that I erased, equation 11 was these properties of alpha and beta minus beta alpha equal 0, and alpha plus minus beta equal delta ij. If you take them, you can prove that this matrix Vij is symmetric. So Vij is equal to Vji, and that must be as it must be. Can somebody tell me why? I say because we are working with bosons. So the interchange of the labels ij should produce no effect on this state. Changing these guys is equivalent, because there is a sum of changing this guy. So if this guy is symmetric, the final state is going to be symmetric, and that corresponds to bosons. And it must be because we are describing bosons. So the conclusion here, I don't write it, but it's the same as before. The vacuum 1, when expressed in the Fock space 2, is a superposition of vacuum, 2 particle states, 4 particle states, 6 particle states, etc. So it's just a superposition of even number of quanta state. And inside each of these states, now you can have quanta with different levels, because look at that we have A daga I, A daga J, and I and J can be different. So we can have one particle, so it's a 2 particle state, but one can have, can travel in this direction, the other one, so they can be different. And these 2 particles are entangled with each other. And so it's a sum of states with some entanglement. And the fact that this entanglement exists will be crucial in the Hawking process and the Unruh effect to obtain thermal results at the end of the day. Remember that Hawking radiation is thermal. This thermality is crucial. It's coming just from the entanglement between these 2 guys. Remember, there is entanglement. When you take the state, you trace over part of it, and you get a mixed state. A thermal state is a mixed state. So what happens in Hawking radiation is that one quanta goes to the black hole, the other quanta goes to infinity. In the black hole, this quanta is lost because it's a black hole, and at infinity, you look at mixed state, which is a thermal state. So that correlations are really behind Hawking radiation. We will see that in some detail, and also Unruh effect. So now some remarks. I am going a bit fast because this is same as we did. If you have questions.
Super quick question. In the fancy alpha and fancy beta, those are matrices made of coefficients of alpha ij and
Right.
beta ij. But in the one right above that, that alpha kj inverse, that's just 1 over that coefficient right there?
Right, they are, if you want, the element ij of the inverse matrix.
Okay, so that one above is an element. Okay.
So you make the inverse of the matrix and take the element ij, that is the alpha that appears there.
Wait, so in Vij equals that, you get the fancy alpha matrix, take the inverse of it,
And
then
you
take
take-
that element?
Exactly.
Oh, I thought it was like 1 over.
And this is
Okay.
why
You
I
wrote it
explicitly
like that.
say that it
Okay.
has to be. And okay, any other question?
I have one other quick one.
Please.
Last time in our simpler theory, we had a Bogomolov type of equation that gave conditions on our numbers alpha and beta. It was alpha squared minus beta
Mhm.
squared plus 1. Do we have something
Yes,
similar?
it's the one that I erased here.
Oh, okay.
It was something like Sam, IJ, alpha, I don't remember. Sam K, alpha K, beta, JK, or alpha here conjugated minus beta equal IJ. That is exactly
Oh,
that.
yeah.
If you put if you remove the indices, you
Oh,
get
that's fine.
alpha squared minus beta squared equal to 1.
Okay.
And the second equation, which I said we don't have an analog in the harmonic oscillator because it's trivial. It's identically 0 for the case of the harmonic oscillator. So now we have this other condition.
Okay.
More comments or questions? So remark 1 is something that you know, that the state 1 is the same state as the vacuum 2. I put same because, U1 is what is really the same. If and only if beta ij is 0 for all ij. This is something that we already knew. No, sorry. What he wants to say the following. No matter, this is the important part, no matter what alpha ij are. I don't have any expression to look at this. But remember that, phi 2 was sum of alpha ij 1j plus beta ij j. This is the part that comes from S1 plus, and this is the part that comes from S1 minus, because this is the basis of minus, this is the basis plus. So it is possible that the two bases are different, but still the betas are 0. So it just, then if the betas are 0, what we are doing is just a change of basis inside S1. If we change the basis, betas are 0, alpha, vacuum 1 and vacuum 2 are the same. So this is telling to us that this implies that the vacuum, the one particle Hilbert space, and the Fock space, let me erase this auxiliary equation, depend on the choice of S plus, but not on the basis that we choose, but not on the specific basis we choose inside S plus, but not on the basis chosen in S plus. Different bases for the same S plus give you the same vacuum. As you expect, because a basis doesn't mean anything. So what means is the space. Physics cannot depend on the basis that you choose. So vacuum is in one-to-one correspondence with subspaces S plus, no matter which basis you want to use. Changing basis inside S plus has beta equals 0, and therefore the vacuum is the same. Is that okay? You look upset? No. And remember, as I said, there is a mathematically precise way of characterizing the subspaces S plus. It's called a complex structure. So there is a one-to-one relation between complex structures and vacuums. And I like these ways of saying things because in physics you always need to find a basis-independent characterization. If you try to characterize something like a vacuum and the characterization uses a basis, I don't like it, because basis don't mean anything. So look for something which is absolute, is objective, doesn't depend on a choice. So this is that characterization.
I have a question.
Please go ahead.
In Minkowski space-time, where time doesn't depend, where time symmetry is preserved, is there only one way to split S plus and S minus? No, there aren't really many. The only thing is that if you restrict to inertial times, if you impose that this guy is made of positive frequency modes with respect to any inertial time, that gives you the same. Okay, so if you want to respect the Poincare symmetry.
Right.
Yeah.
So this,
Okay.
right. So no matter which inertial time you choose, this is what I'm saying. All inertial times, they don't come out from the same S plus, so they define the same size, the same vacuum. Second remark. Just some curiosity. Consider the vacuum two-point function in the Fock space F1. Take the vacuum one and take expectation value with the operator represented, of course, in in the Fock space one. I know that this notation is kind of heavy, but now I want to keep it because we may have confusion. I'll do that. So first of all, it's very simple to compute what is this. Just expand these guys as a sum in modes, and you will get that this is just of course this is evaluated at x, this is evaluated at x prime. It's a 2-point function. So this is what you obtain, and I want you to check that is true, which is half a line computation. And the question is, how is this object, or how this object looks like in terms of the basis phi 2. Still, I want to compute this 2-point function, but in the other basis. The solution is trivial. All what we have to do is to make a Bogoliubov transformation for this guy, and manipulate it. That's all. So it's almost trivial that the solution is interesting. So if you do the computation, the result is the following. The result is the same. So first of all, is what you would get if you compute the 2-point function with respect to the state 2. Plus 2 more terms. I of x j conjugated of x twice the sum k plus another term two times the real part of phi I 2 phi 2j of x and of x prime, alpha conjugated I k, beta conjugated jk, and I forgot to add a sum, minus the sum in k. Can you see that, Rayesh?
Yes. But from now on, if you change the pen, it would be wonderful.
You may wonder why I write this equation, and it's a good question. So I just write it because, for instance, Rayesh will find it familiar, because this is what we find in cosmology all the time. Power spectrum of one vacuum, what you want to express in terms of the other vacuum is the power spectrum of the other vacuum times 2 times beta squared plus 2 times the real part of alpha and beta, etc. So it's just to give you explicitly how to write that, but conceptually it's not really doesn't provide a huge amount of information here. So maybe Prayesh and Srinath find this familiar. So in cosmology, the only thing is that the Bogoliubov coefficients are diagonal. So this is just alpha of k. So everything simplifies. The sum simplifies a lot, and you get what you expect. And this minus and this conjugated is because one normally uses the inverse Bogoliubov transformation, and the inverse of minus beta star is beta. Okay.
Why are they diagonal?
Sorry?
In cosmology, why are they diagonal?
Why they are diagonal? Because the mode carry the mode I over with some k.
K.
They carry an x dependence which is ikx, and this x dependence, if you have a different k, they cannot, they cannot overlap. The overlap is zero, so they are really orthogonal. So the alphas are diagonal because the exponentials are orthogonal to each other. Questions about this? This is what I wanted to say about Bogoliubov transformations.
So what do these two terms represent? Do they represent anything? Just any physical content?
I mean, in simple situations like in cosmology, one can provide some intuition about them. So this is like, but I don't want to put those words right now because I want to be more systematic, and those words are not really precise. This is like the number of particles created, but that is a bad language. So that is what it is.
Are both of the guys in the second term x's, or one of those x prime?
One is prime. And wherever I don't write it, there is an x and x prime there. Yeah. The 2.5 here. So let me move to the other section and talk about inequivalent representations. And as we discussed this morning, I was hesitating how much detail to give on this section because I mean, this section goes very well in this more formal chapter I want to do at the end. But I think it's important to keep the result in mind because it's one of the main features of quantum field theory core spacetimes. So I will do it briefly. So if you get lost, don't worry, just keep that from your mind. I will be more systematic in chapter 10. But at least the main idea is good to have it in mind. And the statement is the following, in last section, we assume U unitary, so this operator, unitary operator, moving from one representation to the other exists. So the question is that true? So and therefore, if it exists, therefore, this state was a state in F2. But that is not guaranteed. So the question is, this is warranted for the harmonic oscillator, for the single harmonic oscillator or a finite number of them. And there is a theorem called Stern-von Neumann theorem. I always spell it incorrectly, so let me check it. There is a theorem called Stern-von Neumann theorem that tells you that if you have a system with a finite number of degrees of freedom, like harmonic oscillator, 5 harmonic oscillator, 10, 100, 1 million, as long as the number is finite, any two representations are equivalent to each other. They are unitarily related. So, for instance, in quantum mechanics, if you work in the position representation or in the momentum representation, they are different representations. Do they describe the same physics? Yes, because of this theorem. This theorem guarantees you that no matter what representation you use, they describe the same physics. And they, position and momentum representation are obviously different. In one, X operator is multiplication, in the other one is derivation, and momentum the same. So they are really different representations, and the Hilbert space is different. One Hilbert space is functions of X, the other Hilbert space is functions of P, but there is a relation between them, and it's a unitary operator, so they describe the same physics. But this is far from obvious, far from being obvious in field theory, when we have infinitely many degrees of freedom. Many is not the same as infinite. No matter how big many is. These infinities mathematically provide tricky problems, and this is one of them. So this Stone-Newman theorem doesn't apply to field theory. So it is possible that this unitary relation between the two representations doesn't exist. And if it doesn't exist, then what? So in this section, I want to investigate under which circumstances U exists, and if it doesn't exist, what are the consequences? So this section want to ask under what circumstances U between the two representations unitary exist. So there are many different ways of proving this. I like more proof which is a bit more formal. But let me do it in a simpler way, which the tools that we have at hand at this moment. And the argument is simple, is the following. So U will exist if acting in any state in F1, or at least in a dense subspace, produces a state in F2 with the same norm. This is what the unitary operator does. It preserves the norm. This is where the unitary condition comes from. So U will exist if acting on any state here will give me another state here with the same norm as the initial state. Second point, that it is not difficult to see that this will be the case if and only if U acting on the vacuum produces a state which has norm 1 in F2. In other words, if we check that for the vacuum, one can see easily that that will be the case. So all what we have to prove is that acting on the vacuum, the resulting state has norm 1. But we know what this state is. I just erased it. It was around here, this exponential of two particle states. So the problem is that we had n in front of it. But n must be a finite constant. So this guy will have norm 1. So in turn, this will be the case if and only if whatever is multiplying that constant has finite norm. The exponential of minus 1/2 h bar sum ij v ij a dagger 2I a dagger 2j acting on the vacuum 2 has finite norm. Because it has finite norm, the n in front of it will be 1 over that, and the state is normalizable to n. So that is the condition. We have to check whether this state has finite norm in the Fock space 2. But this state is of the form vacuum 2 plus some state I want to call alpha plus some state which is alpha alpha plus some state alpha alpha alpha, etc. And I am forgetting 1 over 2 factorial, 1 over 3 factorial, where alpha.
Oh wait, isn't it alpha 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 alpha?
What?
I thought it
Two
did
and
like
four.
powers of 2.
All right, but let me write what alpha is.
Okay.
So, alpha is a 2-particle state.
Okay.
Alpha is 1/2 of h bar ij 2 j acting on the vacuum 2. So alpha is a 2-particle state. So this is 2 particles, 4, 6, etc. Therefore, and this state is orthogonal to this one, this guy is orthogonal to this one, so the norm of this state will be the norm of this plus the norm of this plus, so all the norms. So it is not difficult to realize, this guy has norm 1. If this guy, alpha, has finite norm, we are sure the whole state will have finite norm. So, therefore, U will exist if and only if alpha, so the norm of alpha is finite in the Fock space G. This is what we have to prove. So we can compute what is the norm of alpha. We have 1 over 4 h bar, 4 sums, k m v I j v conjugated mk multiplication vacuum 2 a 2 I a 2j a 2 dagger k a 2 dagger m vacuum 2. Now you can compute yourself that this is h bar square delta ij delta ik plus delta kj delta im. So this is equal. Probably forgot 4 somewhere. No, the 4 is included. If you just do the sum with these guys, you get, and you use the symmetry of V. So use that V ij is equal to b ji. You get just from here with all the deltas. This. The h bar square cancels with this one. The 4 cancels because first of all we have two terms, and that give me a 2, and the other two are the same. So one gets that. Right? Now I can write this in a matrix form. And now I'm going to write the V matrix, just because this is the trace of V times V emission conjugated. Just writing the same in a matrix form, which is maybe more illuminating. So the conclusion is that, therefore, U exists if and only if the trace of V dagger is finite. But remember, V in matrix form, all these are fancy letters. Beta over beta times alpha minus 1 alpha dagger minus 1 dagger. With this, using properties of alpha, so using the properties I showed you before, one can prove that, I'm not going to write it because, but it's simple. The trace of this guy is finite if and only if the trace of beta dagger is finite. So these two statements are the same, are equivalent using the properties. So my conclusion is that U exists if and only if this trace beta dagger, which is the same as sum I j beta I j square, is finite. This is the condition.
At the very bottom left, is that VJI star or VJI? And left more bottom left.
This is a star because I am talking about coefficients, and this is the matrix. So this is the condition. And the statement is that when the sums are infinite sums, this is not trivially true at all. If we have a finite number of degrees of freedom, as long as all the betas are finite, which they must be, this is true. But when I goes from 1 to infinity, that is highly not trivial. So maybe I can just write the conclusions.
Is that the same number that appeared for the number of particles in the, or the number of quanta?
Yes, exactly. So
Yeah.
this is the same as saying that one state has infinitely many particles in
Wait.
the other state.
Is that the same though? Because I have that you had just sum over j.
Right, but I was asking the number of particles in the mode, in one mode.
Right.
This is the total number of particles. So summing the number of particles in the mode 1i for all I. So how many total, what is the total number of particles in any mode? If it is infinite, then U doesn't exist. So that is if you want the physical picture. So I mean, we only have a few more minutes, so I'm not going to give you the formal definition of unitarily equivalent representations. I will do it later in the course. So the statement, the conclusion that we get from here, which is quite important, is that the 1 and 2 representations, fog representations, remember what the representation is a fog space and a representation of phi and pi in terms of creation and addition operators. So are unitarily equivalent, which means that there is a unitary operator that goes from one to the other, that takes the representation of phi and pi in one and gives you the representation of phi and pi in the other. If they are, then physically they are the same theory. Because if you give me any state in one and any set of observables and you compute expectation values, as you were saying before, the unitary operator ensures that there is another state here which has the same expectation values with respect to some operators there. So physically they are the same theory. Any physical prediction you can make here, you can also make here, just bringing the state and the operators with you to the other topic space. But that is only the case if and only if the sum over beta is finite. If that is not the case, then they are unitarily inequivalent. So let me finish the class with some comments. So the first comment is that, of course, only if this condition, this is trivial, condition is satisfied, the state, the vacuum one belonging to the focus space one can be written in the focus space 2. That is trivial because we just said that this is the condition that tells me that the state U, vacuum 1, has finite norm in F2. If it has infinite norm, that means that it doesn't fit, it doesn't belong to that space. So that is true. Second, something just about the condition. So note that the condition is a trace. Right? That the condition is given by a trace. Why do you think is that important? Say it again.
Something to do with entanglement?
Yeah. Because a trace is basis independent. The trace of any matrix doesn't depend on the basis. So in this way, you can have the feeling that this condition depends on which basis I use, but the statement is no, because the trace of beta star is basis independent. So, and the trace is basis independent. So therefore, I don't write it, but it's important. The fact that the statement that the two representations are equivalent to each other or not doesn't depend on the basis. Only depends on S1 plus and S2 plus, no matter which basis you use, as in math league, of course. This is why I wrote this in this explicit form, to show you that this is really a trace. And the last comment, which is, in my opinion, quite important. So, is that we have obtained quite a strong result, or quite surprising result. We have obtained a surprising result. which is that in QFT there are inequivalent representations, quantum Fock representations. And this is, to me, quite alarming. So the picture here is that, you know, you can choose some S class and you can choose a different S class. There is no preferred one. But you may find that your quantum theory and your quantum theory are inequivalent, unitarily inequivalent. That means that the physics of your Hilbert space cannot be reproduced in the physics of this Hilbert space. So they are mathematically and physically different theories. And that is a very surprising statement. So now what?
So
You know, now what? I mean, that is, now what? Quite alarming, you know. If we have a freedom, but the freedom is essential because the resulting theories are physically different theories, then we have here a big problem. And the first point is that this is simply true. And this is maybe the major issue in quantum field theory in core spacetimes, the existence of inequivalent representations at the mathematical level. So, you know, that just, you should keep that in mind. I mean, that is the way it is.
I
I have a
Say
sure.
again?
I have a short question.
I have a short question. So,
If we have
if we have inequivalent Fock space representations,
first
first question: how does that relate to general representation of this algebra of observables? Like, how much is known in terms of classifications of representations that satisfy some criteria? I don't know, irreducible representations, etc. And second question: if we were to try to combine different representations, in what way is that possible? So could we choose, for instance, two inequivalent representation and build probably then non-irreducible, so a reducible representation on the combination, like I don't know, direct sum of the two unitarily inequivalent Fock spaces, or even more.
First of all, you know, when we talk about representations of the algebra of operators, so we have this Heisenberg algebra between Q and P, you know, and you want to study them, what you do is you restrict to irreducible representations. Because if you start with reducible ones, you have, you know, you have more information than what you need to have, and you don't get a clear picture. So all these Fock representations, I haven't taught it systematically. I will do it later on in the course. But all of them are irreducible representations of the computation relations. And the fact is that they are inequivalent. So you know, if you just restrict to irreducible representations, you find inequivalent blends. And so that's the way it is. So
are there more than the Fock space representations? Are there non-Fock space irreducible representations of the Heisenberg algebra?
You can build non-Fock representations. I don't know if you were in the, I know you were in the seminar, in a Vice seminar about black holes the other day.
Yeah.
Remember, he was saying that there are solutions. He was talking about the Maxwell field. Solutions of the Maxwell equations which doesn't have finite Klein-Gordon norm. I mean, not Klein-Gordon, but the equivalent. And therefore, the state that you can build from it doesn't fit in the Fock space, but they exist physically, so in that case, there are non-Fock representations. And, you know, and there is a mathematical way of dealing with all these inequivalent Fock and non-Fock representations, which is what people call the GNS construction. It's called the algebraic approach to quantum field theory. I think I will have time to summarize it at the end of the course, but the statement is that these inequivalent Fock representations exist, There are other non-Fock representations, and all of them can be embedded or treated simultaneously in this GNS approach, in this algebraic approach to quantum field theory. Does this reply your question?
Yes.
So, just to be sure, you're saying that all the representations for like the standard fields or situations that one knows are classified, or to what, like, how much is known about structured classifications of all these irreducible representations, like it's the GNS construction.
I mean, but the classification I think is clear. I mean, I don't know if it happens like with the Lorentz representations that you can index them by a couple of indices. That doesn't happen here, but the properties are known and mathematical are under control, and what this GNS construction does for you is just to treat them all together, even if they are inequivalent to each other, and provide a mathematical sense to all that.
I see. And in physics, so Abai was speaking about how important it is to also include these, I guess, hairs or other states of the Maxwell field in order to make the S matrix well defined. So you really need them and treat them together if you want to make sense of certain operators or scattering amplitudes.
How
exactly do you do that? Like, how do you combine these
My
Hilbert
understanding
spaces?
is that in the scalar field everything is simpler, but in the Maxwell case, what you go is precisely to this algebraic approach, which doesn't really require a Fock space, so they are really a non-Fock approach. But for most of the situation of the scalar theory, like in Hawking radiation, all that problem with Fock representations, we have enough.
And that means you just choose one.
Choose one. And let me now comment, what we do physically with this, because physically this is extremely shocking. And I am out of the time, but let me just one more minute. This is shocking. What do we mean by, all these questions are very well posed. Now what we do? If we have freedom, and the freedom gives you inequivalent theories, mathematically and physically. So your predictions cannot be reproduced in my Fock space and vice versa. So this is a very strong statement. So please remember that. One of the main features of quantum field theory in coarse spacetime is the existence of inequivalent bands. But physically we have a way out, because which maybe is the reason why this, for me, very important fact is not mentioned in the first page of every book. And it's because it has been proven, and I can give you the references, I have them, that, so the statement is that if you take infinitely many operators and you make infinitely precise observations, your numbers cannot be reproduced in my theory. But has been proven that if you restrict to a finite number of observations, so no matter how, take zillion operators, no matter how zillion is, but smaller than infinity, and add some, our observations, real observations are never, have some accuracy. They have some, we can never make infinitely precise observations just because, that is physically implausible. So with these two conditions, finitely many operators, and finite resolution, so finite accuracy, then it is, no matter how small is your accuracy, as long as it's not extremely completely precise, I can reproduce your observations in my Hilbert space. So if I allowed some delta function, some delta in the precision of my observables, and I have a finite number of them, I'm sure I can reproduce your physics in my Hilbert space. So in that sense, these inequivalent representations are, in some sense, mathematical, because at the physical level, in physical reality, we cannot distinguish between them. So if you want to make physical predictions, take any of them and make physical predictions. with a different one, you can produce the same physical predictions with these two conditions. So it's not physically as alarming, it may sound, but mathematically it's quite, it's a quite shocking fact that is the case. So please keep these two statements in mind. They exist mathematically, but they are not destroying our physical predictions.
So does this have any implications for causality? Causality?
In what sense?
It has no connection with that?
No, inside each representation, the theory is causal.
Okay.
Inside the other representation, the theory is causal. The only point is that mathematically, they cannot be related by a unitary operator, so they are mathematically different theories.
I didn't quite understand how the physical predictions came out the same. Is that something you'll be covering later?
How the predictions are the same?
How you can have different representations that don't connect, but then the physical predictions still come out the same. Is that something you'll be?
So in equivalent representations with same predictions?
Yeah.
I mean, I will not prove that because I can give you the reference, but that is, it's extremely mathematical. Even in mathematical books, they refer to the original paper. I mean, that can be done, but it's quite. So I think you will not be happy if I do it in the blackboard.
Okay.
So just, I have the references here, and that is the same. You can prove mathematically that.
It was maybe okay that I didn't understand that.
I didn't explain that. I didn't deduce that. So it's. I mean, I can spend half an hour giving you the summary of how that works and what you have to do to. But the technical proof is quite technical.
Okay, well, we'll skip that then.
Any other question?
Good.
I have a pretty quick question. I'm still trying to just catch up with a lot of this stuff. I gathered, just starting completely fresh, we have a Klein-Gordon equation. Then we saw that we have a specific space of complex solutions to this Klein-Gordon equation. We know we can decompose it in a number of different ways. And we saw that if specific Bogoliubov transformations between two different representations have this property that sum is less than infinite, I can have a unitary operator that can transform one to another.
There is an isometry between the two quantum theories. They are isomorphic to each other.
But there are specific decompositions of the same space of solutions that I cannot choose a unitary equivalent way. Where along this path did I kind of require I needed to be in a curved space-time?
It's the space of solutions.
Okay, so the space of solutions is for a curved space-time space of solutions.
Right.
And in flat space-time, because I still have a space of solutions with a Klein-Gordon.
Right. And the same is true, but somebody will say, there is a preferred one. So forget about the other one. Just choose the one given by inertial times.
Okay, and once I do that, then I can say all my representations clearly have this unitarity equivalence. Well, I could still have the same freedom in my flat space-time geometry to do the same thing and run into a similar problem.
Exactly.
But here, I don't have some sort of preferred sort of choice like I did.
So the problem is really obvious because you don't have any way of choosing one.
Okay.
So I have a question on the intuition of having like inequivalent representation but being somehow similar. So a simple example in flat space-time where we find an inequivalent representation to the standard Fock representation built on a Lorentz invariant vacuum would be one where in the Hamiltonian we remove the derivative terms of the fields such that we have just pi squared plus m squared phi squared without any derivative, which usually we turn into a k squared after a Fourier transform. We just have pi squared of x plus m squared phi. We really just have a collection of harmonic oscillators labeled by the point in space. And if we now, instead of turning phi of k into raising and lowering operators and doing the standard decomposition. We could the same do for phi of x at every point, and we get independently oscillating oscillators at every point. How could I use this Fock space? Like, what is intuitively what I need to do to reproduce our standard physics in this very weird localized Fock space? Do I need to look for a state that is approximately or close to the standard Fock space vacuum, or even though I don't have this state because it would have infinite norm, or what's kind of the idea behind
First of
that?
all, if I understood well your point, you are doing something different because you are really changing the theory. You are going to the Lagrangian and changing the Lagrangian. So you now have two different theories. In what I said, I only have one Lagrangian, one theory, but two different quantum representations. So,
I didn't want to change the theory. I really just you can completely forget about the Hamiltonian and just let me say that I decompose phi of x into raising and lowering operators.
okay, so let me give you the example of the Unruh effect. This is what we will do So in the Unruh effect is the Minkowski spacetime, and you can choose the Poincare invariant vacuum, the standard Minkowski vacuum. But you can also take, the quantum theory formulated by a uniformly accelerating observer. And it's not exactly that because you need the two Rindler wedges, but there is a way of choosing a different vacuum physically associated with observers which are accelerating, and that vacuum is an equivalent. So these two Fock spaces are inequivalent to each other. But the statement is that imagine that you give me 10 observables that you want to pay attention with. And you tell me, this is all what I care. I say 10, you can tell me 10 million. What I have to do is to, the idea is, the idea to embed this other vacuum in the standard Minkowski Fock space, which in principle doesn't fit because has infinite norm. But what I can do is I can decompose this other vacuum in the basis of eigenstates of these 10 millions of operators, and whatever is left, throw it away. So in other words, projecting my second vacuum on the space of eigenstates of these operators, then it will fit in my Minkowski spacetime. So
why does it suddenly fit? You're saying, we are looking at operators that where the eigenbasis is not complete, like
right, because in principle the Hilbert space is infinite dimensional. So when you just focus on the subspace of eigenstates of certain operators, you are just selecting a part of the Hilbert space. So your state, which will have infinite norm, doesn't have infinite norm anymore. But still, it keeps the information for all these observables.
But I mean in principle. But I mean in principle, also the eigenbasis of every operator is infinite dimensional. At what point can you truncate? Is that the fact that you don't measure to perfect accuracy and you somehow somehow truncate the eigenbasis of the operators as well?
Right. So you remove the infinities in that way, getting on a finite number of observables and truncating also the basis that you are just pointing out because of the accuracy, and then you can fit the state on the Minkowski space. That is the intuitive idea, of course, mathematically.
And then you can also do stuff like time evolution of this kind of restricted or projected state, and you get approximately the same behavior. I guess if you evolve the operators somehow, yeah.
Mathematically, it's highly non-trivial. It's finding with infinities, and they are highly non-trivial. But the physical idea is there.
Thank you.
Sure.
Thank you.
So the summary is that exists mathematically, but physically it's okay. So we will start applying this theory from now on and see what predictions it makes. Okay.